So we got one more revenue example to do. The wording's a little different, so let's work with that. The price P in dollars and the quantity X sold of a certain product meets the following demand equation. So X is equal to negative 4P plus 72. And then we have some restrictions on P. P can only go between 0 and 18. All right, and then we're going to basically answer a bunch of questions based off of that information. So P is the price of the quantity of items that we have. And so the first question they're asking is, why is there a restriction on P? Well, if we take a look at the lowest P value at 0, we see that X is equal to 72, right? That's P equals to 0. And at 18, if we plug that in there, X equals negative 4 times 18 plus 72, we basically get a negative 72 plus 72, we get 0. So one of our data points is 0, 72, right? And another data point is 18, comma 0. And so I know I have them kind of reversed, but P is now serving, right, as the x-axis, and X is basically serving as the output. I know it's a little strange. And so we have 0, 72, right, wherever the heck that is, and we have 18, 0, which is down here. So this graph looks something like this. And the reason why we're restricting ourselves to this is because P can't be less than 0, right? We don't want P to be negative because this would make no sense, right? We either we either don't have a price, which is 0, or the price is positive. And then 18 basically becomes a restriction, because if we go below that, then our x's become negative. And since x's are the number of sold, we're either selling something or we're not. So x being less than 0, having negative amount of something, or having a negative price doesn't make any real world sense. So that is why there's I think we call that an implied domain, right? Because we know the function itself goes on forever and ever and ever, but because we're mathematically modeling something in reality, there has to be a restricted domain. And so in this case, by restricting the domain, we're making sure that there's no prices that are negative and no values of quantity that are negative, because they wouldn't make any real life sense. So the next item of forbid is find the revenue R as a function of P. Now from the last video, we know that the revenue is the number of units that I sell, we'll call that X, times the price per unit, and we'll call that P. And we already know, right, that X is equal to negative 4P plus 72. So all I've got to do is replace that X with what we were told, and I got it. So R of P now, right, is equal to negative 4P squared plus 72P. And so there's our revenue function. Unlike the last example where it was dependent on the number of units, our revenue function is now dependent on the price. Okay? And so they're now asking us to find the revenue generated for a price of 10. Well, that's just basically R of 10. So I plug that value in, and I'll do it right this time. I think I did, oops, plus 72 times 10. Sorry about that. This is 100, so this is negative 400, and 72 times 10 is 720. So when I do that, it looks like P of 10 is 320. So, or excuse me, R of 10. So my revenue for a price of $10, my revenue is 320. Again, we'll just assume that's in dollars. Okay, so there's part C. Part D, what price is needed in order for the revenue to be a maximum? Well, again, going back to this equation, we see that it is a parabola, right? We have P squared, and A is negative, so we are basically looking, let me kind of come down here, we are definitely looking for the vertex, right? So what P value creates a maximum R value? So we're basically looking for H and K. So what do we know about H? Well, it's negative B over 2 times A. For my model, B is 72, and my A is negative 4. A negative divided by a negative is a positive, so we have 72 divided by 8, and I believe we get a 9. So the price amount that maximizes the profit, excuse me, the revenue, is 9. Right? So that P is 9. So we know that part. What is the maximum revenue? Well, as we found, right, to find K, we basically evaluate my function at the value that we just found. So we got to find R of 9. So plugging that in, right, we basically do that evaluation. I think this is -4 times 81, and 72 times 9. 9 times 2 is 18. Carry the 1. 60. I get 6480. All right, and then I think 4 and -324 plus 648. And I believe if we subtract those, we end up getting 324. All right, so according to this model, the maximum amount of revenue that we get is 324, and it occurs at a price of 9. So you can see at a price of 10, by raising the price, the revenue has started to go down, right? That's what it looks like we have there. So here's 10, and we already found that value. To get a maximum, I want to basically keep my price right around $9. And then what's the quantity X of items that are sold to maximize the revenue? Well, we can come back up to here, right? We were told that the quantity amount was -4P plus 72. And we know the amount that maximizes the revenue is P equals to 9. So we just substitute that in there, and we find our value. So I think we get -36 plus 72, and we find that X is 36. So there's all our values. So our building of our function, this new idea of an implied domain is important because we're trying to make sure everything remains positive. Our revenue function classically is the number of units times the price. And then there's usually a constraint equation that will help us replace X or P. In the video before, we replaced P, and in this video, we're replacing X with P. And so we get a function now that's quadratic, and we can do all our quadratic analysis or even do some other things with our model. Okay, so there's our first stab at optimization problems in a revenue setting. We'll take a look at some geometry coming soon. New videos coming up.